In this problem, we want to find I of t for t greater than 0. The switch closes at t equals 0, and we're going to have a second order circuit because we're going to have both the inductor and capacitor in the circuit. So we'd have a second order circuit, and we'll utilize our problem solving strategy entitled second order transient circuits. And to start off, we want to write the differential equation for our circuit. So let's look at the circuit for t greater than 0. And we're looking at writing our differential equation. I'm going to utilize nodal analysis. Let's pick this as a reference. And then let's define a node voltage here we'll call V of t. And let's start writing a nodal equation at this node. And if we do that, we'll have V of t minus 10 over 10. That's the current leaving this through this direction. And then we'll have V of t minus 20 over 10. That's the current coming down this way. Then we'll have just I of t, it's this current, and then the current through the capacitor over here will be 0.01 dV dt, and that's equal to 0. Now, let's see, let's collect up some terms. We'll have a couple of 0.1 V of t, so we get a 0.2 V of t plus I of t plus 0.01 dV dt. Now, minus 10 over 10 is minus 1, and minus 20 over 10 is minus 2. And move those over to the right-hand side. That becomes 3. Okay, so again, we've got the case where we've got one equation and two unknowns. If we go up to our circuit, though, we can see that we can write V of t is 2 di dt. So now let's substitute that in to our equation. So we got 0.2 times 2 di dt plus I of t plus 0.01 times the derivative of 2 di dt. So now we've got the substitution. Now let's work with the math a little bit. This term becomes 0.02 d2i dt squared plus 0.4 di dt, and then just I of t is equal to 3. Now let's multiply 3 by 50, and when we do that, we'll get d2i dt squared plus 20 di dt plus 50 I of t is equal to 150. So there's our differential equation for this circuit. Now, step 2 says, well, develop the characteristic equation. The characteristic equation is going to be s squared plus 20s plus 50 equal to 0. And this is characteristic equation, and we'll look at our response in a second, but first we need to find the roots. So if we use a quadratic equation, we have minus 20 plus or minus the square root of 20 squared minus 4 times 1 times 50 over 2. And our roots become S1 is equal to minus 17.07 and S2 is equal to minus 2.93. So we have real roots that are unequal, and then we know that our response, we know that it's overdamped, and it's of the form K1 e to the minus 17.07 t plus K2 e to the minus 2.93 t plus K3. Now this response we're talking about is the natural response. Okay, this is determined by the characteristic equation. This is our forced response. And that's because if we look at our circuit, for t greater than 0, we notice there are going to be sources left in that circuit, and as a result, we'll have some value of DC current flowing at the end, and that's going to be the K3 term. So now, our challenge is to go through and find values for K1, K2, and K3. So let's start. So here we're at step 5. Let's now start at t equals 0 minus. Here's our circuit at 0 minus. The inductor's been replaced by a short, the capacitor by an open. If we look at our circuit, we know there's 10 volts. So we know there's 1 amp. Okay, so the capacitor voltage is 0, and the inductor current is 1 amp. Okay, so there's those values. Now let's look at t equals 0 plus. So here we are, and what we're really interested in is di0 dt. What's the derivative of the current at 0? So if we look in our circuit, there's the capacitor, here's the current here, I of 0 plus, and if we think about the inductor, okay, we would have V is equal to L di dt. So we'd have di dt is 1 over L times V of t, and really that's 0 because if we evaluate this at 0, we know that's 0 because of that voltage. Okay, that capacitor has a value of 0, so the derivative di dt at 0 is 0, and we got that from just using L di dt. Now let's look at t equal infinity to get our final values. If we look now, for instance, by using KVL, we can see there has to be 10 volts here just by KVL around this loop. There has to be 20 volts across that resistor. Again, that's KVL around this loop. So this current's 1 amp. This current's 2 amps. So if we do KCL, that's 3 amps. So that tells us that I of infinity is 3 amps. So now, our response we know is K1 e to the minus 17.07 t plus K2 e to the minus 2.93 t plus K3. And we know I of infinity is 3, and that's K3. And we know that I of 0 is 1, and that's K1 plus K2 plus K3. And then if we go up and take the derivative here, so if we look at di dt, we will have minus 17.07 K1 minus 2.93 K2. And we know that's 0. Now, if we take the derivative of that K3 term, that's a constant. So di dt of K3 is 0. So we get that K1 is equal to minus 0.1716 K2. And now we have so I guess this is di dt evaluated at 0. So now we have 1 is equal to K1 plus K2 plus 3, and we have these two equations. And if you solve, you get K1 is equal to 0.4143. K2 is minus 2.4143. So our solution is 0.4143 e to the minus 17.07t minus 2.4143 e to the minus 2.93t plus 3 amps. And I think if you check the initial condition, that's going to give you the initial condition of 1.